Okay, it's 9:30, so I think we can start this this session. So just to make sure nobody makes a mistake, this is EU3 parallel session of MG16. This is the first block today, which lasts 3 hours from 9:30 to 12:30. There will be a second block tomorrow. This is, sorry, Central European time. And there will be the same time slot allocated tomorrow for the second block. So the session is we'll have today 5 talks, and every talk is allowed 25 minutes of presentation, followed by 5 minutes of questions and discussion, as you can see from the timetable, which is then followed by 5 minutes of what I call the technical break. And the reason for this technical break is multi-purpose. Unfortunately, tomorrow, because there is one extra talk, this technical break will be only 1 minute. But basically, the idea is that, well, we can use this time, you know, to just go grab a coffee or do something 1 minute, or to try while we try the connection for the next speaker, and also to extend a little bit the questions and discussion session in case this is needed. So basically, each talk is separated today by 10 minutes. Tomorrow it will be slightly tighter, and 2 talks will be separated by 5 minutes only. So as you probably know, but I was asked to basically remind this to everyone. These sessions are recorded in both audio and video, and this is also a good motivation to have a little bit extra time to give your presentations, because in this way, if you can provide a gentle enough introduction to the subject, people in the future may watch your video and learn something from it, starting from the beginning of the ideas that you want to discuss. So there is only one, so if you have any questions or doubt, okay, we already tested your connections, which seems all good, and so there should be no problem. In case there will be a problem, we will try as much as we can to accommodate. So if the connection drops, my connection drops too sometimes, but I'm not speaking today, so maybe this is not a problem. So we will wait maybe 1 or 2 minutes so that you can try to reconnect and continue your presentation without having to interrupt it or postpone it. If this will not work, so in practice, we will use these 5 minutes of the technical break to take care of this situation, should they ever happen. If the situation is more serious, like you realize that you cannot maybe connect immediately, or you don't succeed to connect immediately, we will jump to the next talk, and you will be given the possibility to complete or represent your talk at the end. There may be one exception, because there is one talk which I think cannot be moved because of the constraints of other parallel sessions for the speakers, but we will do as much as we can. If there would be some really unsolvable problem today, I will try to see if it's possible to ask the organizers to maybe move your talk to tomorrow by extending the session, although I have to anticipate that I already asked that, and they were very strict about the fact that sessions cannot be extended beyond the time limit, which is set by the organizers. This comes to, I think, what is, I think, the most important point to keep in mind for these parallel sessions is that, unfortunately, I don't have any control on the duration of the session, in particular on the termination of the session. So I don't have the possibility to extend the session if something happens. I think between 5-10 minutes after 12:30, so 12:35, 12:40, I'm not sure, because we didn't have a test of this. The session will be automatically closed, and any talk in progress will be cut abruptly. So I ask you to do your best to keep the time of your presentation in such a way that we everybody can use the time they have been given for their talk. So I don't think I have any other things. Yes, one minor request. So this is the early universe parallel session, and I would appreciate if we use the word early also when we will submit the proceedings for these talks. So like I know that sometimes at the Master Grossman, as you probably know yourselves, the proceedings appear much later than the conference, which is sometimes a pain. Function C are function of time and are. Sorry, I will mute you. Okay, so of course there is I know by first experience that sometimes we need time to fix the material in our presentation to be nicely published in the proceedings. But I mean, if we can be not only early universe, but early submitters of the proceedings, I think this would be very appreciated by the organizing committee. So if you have any chance, please submit your work as soon as possible. And if you are willing to do so, it could be nice also to upload, if you can, through the Indico system, your presentation, or if you don't want to upload all the slides because maybe there is something preliminary that you think is not appropriate to show at the moment, you may slightly modify the slides or present a subset of them which you think is appropriate in such a way that it remains in the record. And again, if some people could not follow your talk because now they are busy with one of the other large N parallel sessions that are running, they can basically come to know your work and your ideas also at a later time by taking advantage that the meeting is online this year. Of course, being online has advantages and disadvantages, but we should try to gain the most out of it. So this was my introduction. So I don't have other things to say. So if you have any questions or doubt or request, please let me know. Otherwise, we will start with the first talk, which will last, as I anticipated before, only 20 minutes, and will start at 9:35 because the speaker is now presenting another talk in another session. So within like 7 minutes, we will start the first talk. And in the meantime, if you have any questions or request, please let me know. So thank you everybody for participating in this session and submitting your contribution. And we will start in just a little bit more than 5 minutes with the first talk as soon as the speaker will join. Welcome also to the people that just joined. So this is the Early Universe 3 Block 1 session of the Marcel Grossman meeting. We are currently waiting for the first speaker that should start his talk with 5 minutes delay because he's currently busy in another parallel session. So he should join in a couple of minutes, and then we will start with the first talk that will therefore last only 20 minutes and not 25. So thank you for your patience. Sorry, while we wait, I have a question. In case, as I mentioned before, there is some connection problem and we need to reschedule some of the talks. Is any of you who has kind of constraints coming from other parallel sessions, or everybody's fine in case some of the talks are slid from one slot to another? Okay, let's say if anybody has a problem, please write in the chat or say something. Okay, so I hope we don't have any complication, but in case, I know that we can reschedule live some of the talks by keeping, of course, the time.
Thank you, sir. I'm ready to go.
Okay.
Thank you, Stefano.
No problem. You're welcome. Okay, you have 20 minutes.
Now let me get my thing up. I'll try to get ready as quickly as possible. I assume that you want to see my screen, correct? Or do you have the uploaded talk? I gave you an uploaded talk.
Yes, but if you can share your screen, I think is the best for everybody.
Can you upload my talk? I gave you, I sent it as part of the, can you do that?
So what would you like me to do to show your?
Well, you want me to, let me just go ahead. I can just locate it on the, I can locate it on the next one. Okay, hold on a minute.
If you can share your screen, you can start your presentation.
Yeah, I can hear you. I'm just going to locate the, I'm going to locate the, my talk. Okay.
Sure, no problem.
All right. Thank you very much, sir. Thank you. You're very gracious. All right. Now, let me see. This is the early universe.
Yes. So now your presentation will be about the non-singular universe model from Rosen and how it can help to solve cosmological constant, dark energy, and arrow of time problems.
Okay. Okay, wait a minute. Hold on. I'm just about ready to come up. Okay. Okay, wait a minute. Wait a minute. Sorry. Just give me a minute.
Yes.
I'm sorry for being so clumsy.
Take your time. We have We have time. We have
just
some
have to
technical
relax
time.
a little bit. I'm very, very tense.
Yes.
Okay. Here, wait a minute. That's not right.
If there is anything I can do to help, please let me.
Okay, I found it. It's a solution of the cosmological constant dark energy, and I found it. Okay.
Yes.
So, which is that I'm clicking on the presenting material. All right. I'm going to download this. I'm downloading this as MG16. All right. This is Rosen, dark energy, time, and other things of sort. It's very well defined. All right. Now, which is that yeah, this is it. Do you see my screen?
Not yet. You will have a share screen button at the bottom of your Zoom window.
This should be green. This is it. Do you see it? Do you see it, sir?
No, we don't see it yet.
What?
We don't see it yet. We don't see it yet. We see.
Okay. All right. I have to quit freaking out. Okay. Dark energy, massive gravity. Okay.
Did you press the share screen button?
I will get it. I promise you, I will get it. Here we go. Yes, I have it. Do you see it? Do you see it, sir?
No, not yet.
What?
No, we don't see it yet.
Okay. Let me open up the screen. Share the screen. Do you see my screen? This is it. Do you see it?
No, we don't see it yet.
Do you see it
now? Okay, now yes.
Great.
Okay, now you're on and your screen is visible.
Here we go. I'm going to get going as fast as I can. All right.
Yes.
So, which is that I'm going to have to somehow move this a little bit over to the side because that you are okay. A solution of the cosmological constant dark energy arrow time using a model of a non-singular universe from Rosen from volume 56, Ettore Batarana in International Science Series Physics 1991. Andrew Beckwith. All right. Now, we reduplicate the book Dark Energy by Lee and Wang, giving 0-point energy calculation unexpected length with an unexpected length added to the width of a graviton weighed by the ideas given by Rosen. All right. Now, so introduction. What we're going to try to do, I have to move this over a little bit to the side. All right. What we're going to have to do is confirm is we can apply the techniques of the following reference to the problem of dark energy in the arrow of time and heavy gravity. The work I did in one was allegedly not credible. So what I did was that people didn't like having multiverses. So what I did was I went back to an old ideal by Rosen, which had a non-singular universe. And I used that as a way to come up with, to say, descriptions about dark energy. Now, the idea is to come up with a mass of mg h times the square root of Planck's constant divided by c. We ask for initial conditions for the arrow of time and this cosmological constant in dark energy formations. methods for determining dark energy and heavy gravity. We'll start the redone calculations at vacuum energy given in 3. And that was, here it is, right over here. And this result is a traditional one that is done, which is the one that has such a 119 times something that's so big, right over there. We are saying we have to consider the dark energy. And so then the equation we have to consider is the wavelength. Can the wavelength in some consideration come out to 10 to the 30 times Planck length, which is about 10 to the 30 times the Planck length rates of a space-time bubble. That is, and so I define what the dark energy wave function width would be, 10 to 30 L Planck. We then have to consider how to reach the experimental conditions for when dark energy is going to be this. Here's equation 4. We are using equation 3. Equation 3 only set, instead of Planck length, it's going to be 10 to the 30th. So yeah, let's have a go at it. So that was, so, which is we have dark energy 4. We're going to see how can we come up with dark energy with a wave functional length, which is 10 to the 30 times Planck length. So that really is the nexus of the problem. We'll come up with the initial temperature of 10. So the idea was what I used what Rosen was referring to, which is one of the earliest non-singular descriptions of quantum, of perhaps a quantum universe that existed. And he came with the initial temperature of 10 to the minus 180 degrees Kelvin. And he did this at Ettore Majorana at a radius of roughly Planck length time and value. And this is absolute 0. The temperature of space-time will be the order of Planck temperature after expansion of 10 to the 30th times from the initial non-singular configuration. So let me go back over this, which is here's the dark energy. Here's the dark energy. This was your dark energy, what you would get. Here we come up with a description of, we could come up with a description of this, but this L Planck is going to be what you would start off with when you have 10 to the minus 100. All right, when you 10 to the minus 180 degrees Kelvin, some almost absolute 0. So then it said when you get a heat up, you would come up with a big entropy value. And I said the situation, this is after you have expansion of 10 to the 30 times Planck length, and that the temperature would be approximately in this situation. This would be approximately equal to Planck temperature. And what you'd have is after you'd have at least an initial expansion, this has been Kolb-Turner. This is the G star of 110. Hence, it's time to do the treatment, the temperature about what it says about entropy and the arrow of time. All right. So then what I said is that one of the reasons that I went into this is the so-called causal set programs, approximation of quantum gravity, or the space-time is fundamentally discrete, and you'd have some sort of a partial ordering. So you'd have to, so what I'm saying is this. Let's go back up to here. All right. What I'm saying is that you would start off with a discrete Planck length in terms of an initial configuration. It would be expanded. It would be expanded, but the initial Planck length would be in this situation a way of determining what you might call an initial grid size. And then, which is, but when you went up to the temperature, when you get through the initial expansion of inflation, which is how, which is at that T3, which is then you start to generate some sort of signals or particles. This is after you have a 10 to the 30th expansion of the initial space-time. Now, which is, let's go back to what I said about causal sets. The causal set is the approach to quantum gravity. And I'm saying how you start the causal set program would be the first, what you might call length of that sort of thing, would be actually given right here. Let's go back to equation 3. And so I'm saying I'm picking for the causal set L Planck. But I'm saying, which is something we can actually phenomenologically measure for dark energy, that we would have to have a big expansion. So, which is that I went through a derivation. This is the derivation. I just repeated what was done so that Rosen came up with that value, and which was that it's in my it's in what I gave. Now, analysis of the interrelationship between terms of the inflaton for cosmology in homogeneity and temperature T at the pre-matter radiation boundary. We'll set forth the following relationship. Now, here we go again for h bar squared for phi dot 10 to the minus 5 h bar 1.66 g star. That T temperature would be explained when you get up to something like 10 to the 30 times L Planck. The MP would be Planck length. That's what you were doing. This would be fitting into another thing to the sort. This would be fitting into what you might call how you would pick an inflaton. Well, when you do that, other thing to the sort is that when you put all that information about a choice of inflaton, h bar divided by phi dot, the time derivative, this 10 to the minus 5, this is the configuration of what you'd have to be fit in. It's very, all right. So what you're saying is that is you have a very large coefficient of B for the expansion. It's not infinite. One of the questions which I tried to address, is how you could come up. They say, let's look at this. This is one of the things which I identified with using inflaton and everything, sort of 10 to the minus 5. 4/5 B naught squared. This is B naught, this is an initial configuration of potential which you could work toward. And this B naught would also say a lot about dark energy. Now, what does equation 5 say about the arrow of time problem? All right, well, let me just go back to equation 5. All right, what does this say about the arrow of time? Right? So let me get back up here, the equation 5. All right. The situation, what it says is that if you have, let's say, an initial grid size, but then you have a physical expansion, so you have T3. You have T3 would be initially to say at the beginning, this is saying, in effect, when you have an initial grid size of Planck size, but it gets expanded 10 to the 30th is what you would get, is that orderly expansion, what you would have, would fulfill what you might call T-Hoo's criteria. They say for an orderly expansion of the universe commensurate with an actual working Planck's time zero. And the reason was because of that non-zero, but very closely, L Planck that was picked was one of the initial conditions that T-Hooft mandated for coming up with a physical description of the arrow of time. He wanted to have a non-zero, but a definite initial special condition. And he wrote it in a Frontiers of Physics article on that, which is quoted, which is in my references. Now, which is, there's more to the paper than this, but let me get to the final part to it. Because there's a lot more to it than this. All right. Now, which is you have E, which is proportional to a constant, say like KB over 2 times some to T to an alpha. The reason why you said is the question is it can this in some way bits and or information independent to say of entropy? And this is Seth Lloyd. But what I'm saying is that when you come up with that value of what E is right over here, it's in effect specifying, which is that when you come up to the formation of dark energy, is that you're going to, at that point, be having, that E proportional to is something concerning time. I mean, temperature. That you're going to have specified at the end of that initial expansion a bet and other things. I've not seen this done by other people. And here is an example. I'll keep going back to EKB, dimensional space-time, temperature divided by 2. All right. Here we put that in. Here is 8. This is the bits. All right. Now let's go back to what I was doing. And Tihu said that you needed to have a special initial condition. I'm providing a special initial condition. And this is with respect to how here's the T4, here's the other things. This is how you would bound it in. Why would this be important? Well, because of the fact I go back to what I go back to my main point, which is right up here. My main point is the existence of this dark energy right over here. When you have a process, the L Planck would be the temperature would be initially almost 0, but you have a monotonic increase. So when you got something that's very large, it is no longer 0, but it's extremely large with respect to Rosen's cosmological solution for non-singular beginning. Then, which is you start fitting in the requirements. And this right over here would be a way of fixing the problem that everybody's had with respect to this little calculation right over in here. So that is what I've been trying to talk about. Now, there's more to the article than this, but I wanted to stop here and I want to leave the floor open for questions. I'm inviting questions, sir.
Yes, so sorry, if you want, you have another 2 or 3 minutes of time that you can use if you want to.
I'm very hearing impaired, sir. You're going to have to speak up. It's not you. I'm legally very hard of hearing.
Yes, can you hear me?
Yes, I can. It's not you, it's me.
Okay, so you have still another couple of minutes if you want to add something, and then we can start the 5 minutes questions and discussion session.
Yeah, but what I'm saying is that what motivated my approach, let me tell you what motivated it from the very beginning. Because I looked at Tihu's minimum requirements for an arrow of time. The arrow of time wanted to have a specialized initial condition, not a general, but a specialized initial condition. Preferably something that would involve non-zero type of quantities and other things so that they might be close to 0, but then you had a monotonicity, some sort of a monotonic progress of what you might call temperature. So that's what Rosen's criteria provided. That's what Rosen's criteria provided. So that's one of the reasons. The other thing is that it would be closely connected, let's say, with a so-called quantum gravity grid, like the program of, the quantum gravity grid. And so it's an argument that LP, what you would get right up here, this LP in equation 3, at the point where you had temperature would be almost 0, not 0, but very close to it. And you have Planck temperature. I mean, you have Planck temperature after this expansion would in effect, because when you had L Planck or something like that, that this itself would be satisfying one of the conditions that, well, let me just get to where it is. I'm going to point to it. Causal sets, all right? The other motivation behind my idea was to talk about causal sets in terms of quantum gravity. And you'd have, if space-time is fundamentally discrete, how could you come up with the discrete structure of space-time, all right? That was the question. The answer I have, in order to come up with is to go back to is to go back up to this equation 3. You understand that was a very serious motivation behind it.
Okay, thank you.
All right.
Okay, thank you. And so thank you for your presentation. Now I would like to ask if anybody has any questions or comment, and we can have about 5 minutes.
You can always email me at rwill9955b@gmail, not GMAI. I don't know why I did that. That was the craziest thing I've ever done. gmail.com, rwill9955b@gmail.com. Send me any questions that you can. I'm going to try to house break this and make this, since I've talked today, I'd come up with a very succinct idea about how to present this in conference proceedings, you know, to answer all the questions. Do you understand?
Okay. Yes.
But what I'm saying is that I didn't pick this thing about Rosen for fun. You understand what I'm trying to tell you?
Yes.
That was picked for a very serious reason. And the idea was to come up with, I was arguing that L Planck was the so-called baseline, they say, for a grid. This right over here, L Planck, which is, we're looking at it.
Yes. So let's see if somebody has any questions at the moment that you maybe can answer. Let's give, maybe somebody has a question, please type in the chat, or just unmute your microphone and ask to Andrew any questions or doubts that you may have.
Yeah, well, I want to thank you. I am honored to be part of your session. I really thank you and all of you for allowing me to present. I have something about curved gravity in a quantum mechanic, which is my next one, which is actually, in some sense, is simple, but it's very startling.
Yes, so if there is no other question,
that's the thing about the so-called curved space solution to the Schrodinger equation.
Yes. Sorry, if there is no question from anybody, I just have something that I missed at the beginning. I didn't understand at the beginning if you were giving a mass to the graviton in some sense, or if it was the standard graviton like in general relativity.
Well, that is debatable, because the fact is that you've had scaling. People have had scaling to say, well, did that so-called cosmological constant or that vacuum energy, did that come up to say, was the so-called cosmological constant or the vacuum energy varying over time? There have been questions, did you have that as a mass? That itself was really not the main point of my talk. That was just a consideration to throw in, because the people use it as a sign point for massive gravity.
Okay.
My main point of the talk is not massive gravity. It's with respect to the arrow of time. It's respect to other things which I tried to bring up.
Okay, thank you very much. So if there is no other question, let's thank...
I will prepare for my next talk, and I will do everybody the favor of downloading that paper so people don't have to put up with my nonsense.
Thank you very much. So we will have a talk.
Thank you very much. I'm honored to
yes.
be part of your session. You're a gentleman.
And so we can, I will stop your share screen so that we can give the possibility to start sharing the screen to the next speaker. So the next speaker will be Ashu Kushwaha, who will talk about helical magnetic fields and their connection with baryogenesis.
Thank you. I'm going to locate my next thing about, it's shorter than this one. It's shorter than this one, but it has a very interesting point to it, which I'll raise, and I will get to that. So thank you very much. I really appreciate, and I'm honored to be with you.
Yes, if you can please terminate your share screen by clicking stop share somewhere.
Ashu Kushawala. Ashu, hi.
Sorry, Andrew, can you please stop your screen sharing, or maybe I can do it for you.
All right, let me just go get my next talk ready so I don't waste everybody's time, okay?
Okay, thank you.
I'll be ready for you.
Later.
Thank you. I'm honored to be here. Thank you very much.
Later.
All right.
Okay, Ashu, sorry, can you please unmute yourself?
Yeah.
Okay, very good. So we are a little bit early. Okay, good. The 5 minutes of technical time allow us to keep the schedule. So please feel free to do as you prefer. If you expect that somebody may join exactly at 10:15 to listen maybe to your presentation, you can choose to wait a couple of minutes. Otherwise, you can already start and maybe we can have a little bit extra time for questions and discussion after you finish. Okay, so anytime you feel, please start. You can start your presentation. Thank you.
Yeah. Okay. So can I start now?
Yes, sure.
Yeah. So first of all, I would like to thank the organizer to give me this opportunity to present my work in this huge platform. So the talk will be based on these two papers where in the first one we have shown that with the Riemann coupling we can generate a helical magnetic field of significant strength over 3 important length scale, and the model does not have a back reaction problem unlike other models in the literature. And then we extended the analysis and showed that we can actually use the presence of helical magnetic field to solve the baryon asymmetry problem. So in my talk, in the first couple of slides, I will try to give you a basic idea of the helical magnetic fields and baryon asymmetry problems, and then I will try to explain our work on helical magnetic fields from Riemann coupling and the baryogenesis. So let me begin with the two unresolved problems in modern cosmology and particle physics. So observation shows that there is a microgauss strength of magnetic field present in galaxies and galaxy clusters, which is coherent over some kiloparsec to megaparsec length scale. Here by coherence, I mean the length scale over which there is a uniform magnetic field. Now, as you can see in these figures, these are basically the optical images. On top of that, there is a radio signal which is superimposed. So these contour shows the total radio emission, and this dotted line shows the magnetic field vectors. So the problem is that we do not know the origin of magnetic field in these regions. In the sense, there is no compelling theoretical model which can generate the magnetic field of the significant strength over a large coherent length. There are various models. All of them have their own problems. So, but the widely accepted paradigm is that these magnetic fields are of primordial origin, which further amplified due to some dynamo mechanism or structure formation processes. So in this talk, I'll be mainly focusing on the primordial origin of these magnetic fields. Now, second problem is the origin of matter-antimatter asymmetry in the universe. So, which is characterized by this baryon asymmetry parameter, which is the ratio of the baryon number density to the photon number density, that is of the order of 10 to power minus 10. So historically, this value is determined by using the Big Bang nucleosynthesis, where this is, you can see in this figure that the abundances of the light elements depends on the are sensitive to the value of eta, which is the baryon to photon ratio, and these curves are the theoretical predictions, and these yellow boxes are the values which are consistent with different measurements. Now, over the last few years, CMB has given us an independent probe of this number, which is, you can see that this Doppler shift of these temperature fluctuations is sensitive to the value of eta. Now, this shows that there is a asymmetry between matter and antimatter. In the sense, we have more matter than the antimatter. Now the question is how this is a problem. So the problem is that in the modern understanding of the cosmology, the success of inflationary theory suggests that any baryon number density or any baryon asymmetry created before inflation or during inflation will get diluted due to the rapid expansion of the universe. And hence, after the end of inflation, we will have negligible baryon number density. So from that epoch, how this small number is created, which we observe today, is still an unresolved issue for last 50 or 60 years. So there are various theoretical models but most of the models must satisfy these Sakharov's conditions, which in this remarkable paper in 1967, Sakharov proposed 3 necessary conditions for creating baryon asymmetry, which is the first one is obvious. If we start with a 0 baryon number density, then we need some baryon number violation to have some non-zero baryon number density, which is the first condition. And the second, there must be some charge and charge parity violation. This is necessary because this charge and charge parity symmetry distinguishes the particle from the antiparticle. So if we have a 0 baryon number density at the beginning, then the particle and the antiparticle would produce with the same rate, and again we will have this 0 baryon number density. And third is the departure from thermal equilibrium. So in 1996, Sasha Davidson interestingly pointed out that there is a very interesting relation between the primordial magnetic field and the Sakharov's condition. What she argued is that due to the presence of primordial magnetic field, there must be some out of thermal equilibrium dynamics. And since magnetic field is odd under C and Cp, I will again come back to this point in a later slide. This by odd, I mean this B changes the sign under charge and charge parity transformation. So, and hence the presence of magnetic field in the universe violate the Cp violation, which is the second Sakharov's condition. And the third is that since the magnetic field is a vector quantity, and which means it will choose a particular direction and hence breaks the isotropy of the universe. Now, if we want to map this Davidson's condition with Sakharov's criteria, then we'll see later that there is a missing key ingredient in this mapping, and that missing key ingredient is the helical magnetic field. So I would like to spend some time in discussing what is the helical magnetic field and how they are different from the non-helical magnetic field. So the electromagnetic field has 2 transverse degrees of freedom, which we can associate with the left circular and right circular polarization. And for a massless particle, the helicity is basically the projection of the direction of spin along the direction of propagation. And hence we will have either +1 or -1 corresponding to the right-handed and left-handed helicity modes. Now, if these modes are propagating, if these modes have the same propagation, by propagation I mean the speed or the dispersion relation, then these modes will lead to the non-helical fields, the non-helical electromagnetic fields. And if the propagation is different, which we lead to the magnetic fields of helical nature, electromagnetic fields which are of helical nature. So if this polarization modes propagate differently, then we can say that there is a helicity imbalance between both the modes. Now, the question is how we can create the helicity imbalance in a theory, in the sense in the model. So let us consider this Lorentz force. If we make a parity transformation, which is the change of sign of the coordinate system, then the left-hand side will go F as -F. And hence we can see that the electric field goes as -E and the magnetic field remains invariant. So if we look at the standard electromagnetic action, which is a quadratic in electric and magnetic field, which means it is invariant under parity symmetry. But if we consider the contraction of this electromagnetic field tensor with its dual, which is defined in this way, then we can see that this parity symmetry is violated. And hence, we can say that by introducing this term or this term with some coupling function can create the helicity imbalance in the theory. Now, there is a very interesting quantity related to this f mu nu tilde, which is the magnetic helicity, which is also defined as a volume integral, special volume integral of A dot B, where A is the gauge field, the vector potential, and B is the magnetic field. So this quantity represents the twist or linkage of the magnetic field if we talk about in terms of the topology. So as you can see that these blue and red, these are two magnetic flux tubes, and there is a twist in this tube. So if we separate these tubes, then we can see that there is a linkage between these two magnetic fields tube, and this magnetic helicity is nothing but twice the magnitude of the magnetic flux of the first tube times the second tube. Now the question is how we can map these Sakharov's conditions with the Sakharov's criteria with the Davidson's condition, and what is the missing link between them. Now, as you can see, if we have a charged particle which has a positive charge, then from thumb rule we can see that there is a magnetic field in the upward direction. Now, if you make this charge or charge parity transformation, which means this positive charge will go as a negative charge, and we have the magnetic field in the downward direction, which means it breaks the presence of magnetic field breaks this symmetry. And also, as I mentioned in the previous slides, that there should be some out of thermal equilibrium dynamics. So the only condition which is left is that the baryon number violation, which is the first condition of the Sakharov's criteria. So in order to understand that, so the basic idea is that the presence of helical magnetic fields led to non-zero Chern-Simons number density. The Chern-Simons number density is nothing but this term which I have shown here, which is related. Chern-Simons number density is related to this term. So and eventually it will lead to the change in the Fermion number. So if we look at the chiral anomaly equation in the presence of electromagnetic field in the curved space-time, then it has this form which is given in equation 1. The first term is the contribution from the curved background, and the second is the contribution due to the presence of electromagnetic field. Usually this chiral anomaly, this equation is conserved in the classical theory, but in the presence of electromagnetic field or in the arbitrary curved background, this is not conserved. That's why this is called the chiral anomaly. So as you can see that up to first order, the RHS term in the flat of our W universe vanishes, and hence lead to the so these term actually gives a contribution only at the second order, or lead to the these gravitational fluctuations lead to the gravitational birefringence, and which is discussed in this paper by Alexander and Peshkin and Sheikh Zabbari. So the second term, the second term on the RHS in the magnetic field background is non-zero. So that's what we assume here, that there is a magnetic field, helical magnetic field in the universe, and then that's violate this lead to this chiral anomaly. Now, if we write this equation, take this the vacuum expectation value of the zero component, then you can see that this is related to the baryon number density, and which you can see that you can write it in terms of this quantity and then NCS, where NCS is the Chern-Simons number density, which is written in terms of A plus minus A minus. So because of this minus, you can see that if the helical modes evolves with the same propagation, then both are same, and hence it will lead to the zero number. And zero means there is no baryon number density, which means NB equal to NB bar. That implies that there is no baryon number violation. But if we have a helical magnetic field, then this quantity is non-zero, and there is a imbalance between NB and NB bar, because this quantity is non-zero, and that is the lead to the baryon number violation. Therefore, the requirement of the helical magnetic fields to have this non-zero Chern-Simons number density is missing in the Davidson's condition. Now, I would like to discuss what are the problems of magnetic field generation during the early universe. So, in particular during inflation, says we know that the standard electromagnetic action is conformally invariant. So, if you consider by conformal invariant, I mean, if you make this conformal transformation where the metric will rescaled by this factor, which is a space-time dependent quantity, then the standard electromagnetic action in a FIW universe is same as in the Minkowski space-time, and hence these magnetic fields will decay very fast. So in order to get a magnetic field of significant strength, we need to break this conformal invariance of the electromagnetic action. That is the point number one. So in our model, as I mentioned, that to have this to generate this helical magnetic field, we need to have one more condition, which is the parity violation. So which we have introduced in our model. That in our model, the conformal symmetry is broken due to the presence of Riemann tensor, which is not invariant under this conformal transformation. So the our model satisfies both the necessary conditions of conformal invariance breaking and the parity violation. This is the term, the last term, which we have added in the action. So there is this Riemann tensor, and M is the energy scale of the of this term, or the parameter of the model. We have shown that this term at the current epoch, this coupling term is very small, as 10 to the power minus 59, and hence we again after this at late time we this standard Maxwell electrodynamics. Now, if we solve this equation and get the evolution equation for power law inflation, we can the super horizon mode is given in these 7a and 7b equation. Now you can see that this is for the positive helicity mode and this is for the negative helicity mode, and both are different in the sense there is this minus iota in the red, which is different in both the modes. Now, if we plot these modes where the time goes from right to left, then for the positive helicity mode, this you can see that this negative helicity mode is decaying and positive helicity mode is approximately constant or increasing. But because of these different scales, it is looking as approximately constant. So for this value of this parameter is 10 to the power 17 GeV. We have plotted these figures, and this is alpha equal to minus 0.53 is the slow roll inflation case. So we can see from these figures that we can ignore the negative helicity modes, and it is decaying over the period. So we can calculate the electromagnetic energy density for different values of alpha, but for slow roll we have shown that this energy density of the electromagnetic field is of the order of 10 to the power 64 GeV4 in units of d by electron volt power 4. And if we calculate the ratio of the total energy density of the inflaton of the energy density of the electromagnetic field with respect to the total energy density of the inflaton, then we see that this is very small. In the sense, there is no overproduction of electromagnetic field. That means our model does not have any back reaction problem, unlike other models in the literature, where we need to tune the parameters of the model to get this back reaction peak. Now, assuming that there is an instantaneous reheating, we can calculate the value of this primordial helical magnetic fields on the gigaparsec scale, which is of the order of 10 to the power minus 20 Gauss. And on the megaparsec scale at CMB, we get this value as a 10 to the power minus 14 Gauss. And these numbers are within the upper bound, which we know from the various constraints. Now, now I will discuss how we can use these helical magnetic fields to solve the Perturbation problem. So As you can see in this figure, this is a typo. This is a physical length of the universe and divided by this astronaut years. So the modes which leave the horizon early will re-enter the horizon very late. So in our model, we are focusing on the modes which left the horizon very late. In the sense, these are the modes which are responsible to for creating this baryon asymmetry, because these we want our model have this variogenesis which happens at a very large at a very high energy scale. So we are focusing on these model roughly 5 to 10 e-folding. So assuming that there is no significant entropy production after reheating phase, so we are assuming that there is an instantaneous reheating, we can calculate the baryon asymmetry parameter, so which is given by eta b equal to nb over h, where h is the entropy density. So we can and this capital M is the parameter of the model, and MP is the Planck mass, and lambda is the upper limit of upper cutoff of the scale of the baryogenesis, and T reheating is the reheating temperature. Now, using this parameterization, we get this equation 13, and if we plot these numbers, then we can see that for lambda equal to 10 to power 14, we get these the baryon asymmetry of the universe, which is between 10 to power minus 10 to 10 to power 9 minus 9, which is what we observed from the experiments. So this analysis shows that the m equal to 10 to power 17 GeV, which is the scale which we assume is consistent with baryogenesis. And so to conclude my talk, in our model, there is no strong coupling problem because we have not introduced any extra degrees of freedom, in the sense we have not introduced any coupling with the scalar field. So as you have shown that since the curvature is very large in the early universe, the coupling term introduced the non-trivial corrections to the electromagnetic action, and we have explicitly pointed out that there is a missing key ingredient in the Davidson's condition, that is the requirement of helical magnetic fields. And the baryon asymmetry parameter predicted by our model is independent of any specific model, inflationary model, and the reheating dynamics. Currently, we are studying the effects of this asymmetry by considering the quarks and leptons during that epoch. So, yeah, thank you for listening.
Thank you very much also for staying comfortably in the time that you had. So if there is now any question or comment or something, please unmute yourself and ask, or well, if there will be a superposition of questions, please, I will ask you to type in the chat so that we can keep some order. Okay, if there is nobody that has the question at the moment, I have a couple of maybe simple questions. So at the very beginning, you mentioned there is no back reaction problem in your approach, and I just would like to ask if you were referring to the existence of strong coupling between scalar field and electromagnetic field, or if there was something more related to the gravitational sector for this back reaction issue. So if you can kind of elaborate on this point.
So the strong coupling problem mainly arises if there is a scalar field or any field which is coupled to the electromagnetic field, and okay. then the coupling function so creates this strong coupling problem, in the sense that during the inflation, the coupling between electromagnetic field and the inflaton field, for example, becomes very large, so that the theory cannot be treated perturbatively in the sense. So the back reaction problem is which is the overproduction of this electromagnetic field. So if the electromagnetic fields are produced in a large amount, then which is greater than the background energy density, then that can affect the inflationary dynamics. So the relation, if you are asking that is there any relation between the strong coupling problem and the back reaction problem, is it your question?
Yes.
Okay, so as such, there is no direct connection. As far as I know, there is no direct relation between these two problems. The problem arises that this coupling function, we choose this coupling function if to avoid this strong coupling problem. So the problem arises that if we choose this coupling function in such a way that there, in the sense, there are models where both the problems can be avoided simultaneously by choosing particular behavior of this coupling function. So in that case, there is no strong coupling problem as well as the back reaction problem. But as far as I know, there is no direct link between these two. But I have to think about it. I mean,
okay,
yeah.
thank you. That was very, very clear. Thank you. Is there anybody else who has any questions or comment? Okay, so maybe I have another just very, very kind of simple question. So I'm sure that this is kind of a rhetoric question, but there are clearly some constraints, if I remember correctly, that are put on Chern-Simons terms and parity violating terms due to CMB observations. Do you know if all the results that you have are consistent with these constraints, or are you planning to maybe, if not, are you planning to check? I'm sure they are not maybe for your exact model, maybe for other models, but in principle, people asked this question. So I was just curious if you have some kind of a phenomenological, observational kind of contact between your model and existing observations or future observations, maybe.
So that's a very interesting question. So we have not looked at the constraints on this Chern-Simons theory in this work, but in the current work we are trying to look at various other constraints. So in this work we have mainly looked at the constraints on the magnetic field. So because we have assumed that there is a magnetic field in the universe and that can solve this baryon symmetry problem. So we have mainly focused on the constraints on the magnetic field. In the current work we are looking various other constraints. So but we have not we haven't thought about this constraint on the Chern-Simons number density in this constraint on Chern-Simons theories. But yeah, we will definitely thank you so much for asking this question. And
okay.
the first question you asked about this whether these two problems are separate. So I can just make a remark in the sense, as you can see that this strong coupling problem arises due to this by introducing these extra degrees of freedom in the theory. As in our model, there is no such scalar field which is coupled with the electromagnetic field. That means there is no strong coupling problem for obvious. But in this model, we can also have this overproduction of the electromagnetic field. If we lower down the value of this capital M, which is the model of the parameter, then for example, M equal to 10 to the power 14 GeV, which is the energy scale of the inflation, everything just blows up in the sense the magnetic field, which will be very huge. So there is no strong coupling problem, but again you can see that by just taking a lower value of this M, we can have a huge back reaction. So as I mentioned that as far as I know, there is no direct link between these two.
Okay, thank you very much. We have still a few minutes if anybody has a question. Okay, I have maybe a silly comment, then myself again, sorry. If you can go back to the action that you used. This I'm not so sure what I'm speaking really, but so I think there may be some papers that discuss. So basically here you're having some non-minimal coupling between the electromagnetic field and gravity, right? Which is conformally breaking, and you explained very well all the technical details. So I think at this stage, you basically, if I understand correctly, you basically, in some sense, postulated this action because it does well it has all the properties that satisfy the previous requirements that you discussed. I'm not sure what I'm speaking really, but I think that maybe there are some papers that discuss if these kind of couplings could come in connection with positivity bounds when you try to consider gravity and maybe coupled to the electromagnetic field as an effective low energy effective field theory, and you try to find UV completions. So my comment is just that it could be interesting, maybe if you didn't do that already, but maybe you can look if maybe some of terms like the one you need could be actually required not only phenomenologically, but also from some, some approach where we try to construct UV completion quantum gravity theory starting from low energy effective theory. So this is not, I think, something which is necessary. Your work is standing very well by itself. But I think I saw in some papers that were discussing these terms like similar to this one.
Perfectly right. In the sense, it is very nice remark in the sense, recently there is a paper by a German group. I just remember the one guy, Zavi Sera or something. There are 3 authors in a paper. So in that paper, authors have shown systematically by using this effective field theory of gravity coupled to the standard model of particles. So they have shown that at mass dimension 6, if we take the modification to the mass dimension 6, there are these terms, the Riemann tensor or the dual of the Riemann tensor. Particularly, they have taken the Weil tensor, which is coupled to the standard model boson. So here, for simplicity, we have taken that standard model boson is the U1 EM, which is the electromagnetic field. So they have also shown that if we consider the coupling from this higher dimension, in the sense dimension 8 operator, then these fermions and Higgs boson, these things will play an important role in the total action. But at mass dimension 6 operator, in the effective field theory of gravity coupled to the standard model of particle physics, these are the only terms, all these terms with these bosons are different for SU2, SU1, or U1. So yeah, this is what they have shown in that paper. They have also looked at the UV completion, but I am not aware of that because that is a very huge paper. I have not looked at that paper. I have not finished that paper in the sense. Yeah, but I will definitely look at this. Thank you so much for this comment.
Okay, thank you very much. Very good. So I think we have finished the time for discussion. We have still 3 minutes before starting the next talk. The next talk, if I remember correctly, is by Andrew again. So Andrew, if you are here, please share your screen, and you can then start your presentation. We can have maybe, while this happens, 3 minutes short break if you wanted to take something, some coffee or something. We will start as planned in the schedule at 10:50 with the next talk.
Excuse me, Stefano, who is the next speaker?
Sorry, I am back.
Excuse me, Stefano, who is the next speaker?
You are the next speaker.
Is it me?
Yes.
Okay, here I go.
Unless I'm making some crazy mistake, but I think it's you. Yes.
Yeah, I know. I'm going to go. I have the pre-Planck Schrödinger equation here. Let me get this thing up. There it is. And let me get rid of this. And all I have to do now is share the screen. And here it is. Do you see it?
Yes, yes, we see it. Thank you.
Thank you very much. I really appreciate it. Let me just increase the size of this right over here a little bit.
Okay, thank you. So the next
can you see it clearly now?
Yes, we can see it clearly. Yes.
All right.
If anybody cannot, please speak up. So the next talk will be by Andrew again, and he will speak about some study of the Schrödinger equation in pre-Planckian space-time and its talk connection with the early universe. So please start as before. You have, well, you know the time you have, basically. So 25 minutes, in case I will tell you at 5 minutes from the end.
All right. May I proceed, sir? Do I have permission?
Yes, sure.
Thank you very much. Title of my talk, Examination of Schrödinger Equation and Pre-Planckian Space-Time Early Universe. Now, which is that we all know about the Wheeler-DeWitt. This is a different approach than the Wheeler-DeWitt. Now, what I did, I looked at a person named Victuli, write up a generalized Schrödinger equation, which is Ricci scalar inclusion and curved spacetime. This has a simplified version and pre-Planckian regime, which leads to comparing a resultant admissible wave function with Bohmian reformulation of quantum physics. As was done earlier, we compared the result with a formulation of a modified Poisson equation for Poisson-Wolf from 2014, and then used in Flaton physics. The resulting in Flaton is then compared to the wave function on the first part of this document. Thank you. So those are the key words. Now, let me begin. All right. I just want to make certain this is large enough. Victuli treatment of Schrödinger equation for curves space-time. So then what he did is he took something that's nothing that's very startling, IH partial t with respect to a wave function minus h bar of 2m plus mc squared phi, and he made a following substitution. This is what you might call the put, this is, and also to, this is done what you might call perhaps to put in what you might call initial conditions of space-time curvature n. Then it's a more was able to come up with the following result, and this is using the Ricci tensor, and this is again is Bernoulli, and I've actually done the derivation myself, and I vouchsafe for it. Now, what I said is that this equation 3, people are going to look at it and say, goodness gracious, no one can do a damn thing with it. It's a monster. It looks very much like Schrodinger's beautiful equation where he tried to go into relativistic effects, only except that they didn't commiserate with respect to experimental conditions, so he went to the non-relativistic. So when looked at, they said, my God, no one can do anything with equation 3. So I said, try to simplify it. We will rewrite equation 3 with the results of pre-Planckian spacetime. Partial 4, 4r mc h bar partial r squared 5. Let's right over here. Here's RCA becomes a constant as how the wave function evolves, and our candidate wave function takes this form. So in other words, what we did is that here is what Bernoulli came up with, so I confirmed it. And then the approximation is in pre-Planckian is to assume that this sort of a constant, this sort of here, really in a pre-Planckian case, is going to be a good approximation, almost a constant term. So if you do something like that, you could come up to say with an initial wave functional form that look at equation 5. We'll be identifying what to put into the Ricci scales given the pre-Planckian spacetime. So this is what my candidate solution was, and this is what I put in. So here is what I said. We want to have this put in initial, and you're going to come some, and I'm assuming is that you have a pre-Planckian bubble, a space-time, and they get the A initial is going to be scaled to something like 10 to the minus, 10 to the, it's just going to be 10 to the minus 25 or so. It's going to be something enormous. So what you said is you do something like that and have that approximation. What you find out is the 6K was the curvature, and is going to be a dominant term. So then it's finding the initial value of equation 5 right over here. What is the initial value of it? Well, in order to do this, it may be useful to look at classical degeneracy arguments for firing, and the initial for Rubicode may be useful for that. And so what I did was that what I was able to come up with in terms of initial wave function was to use a semi-classical argument. And I know that there are lots of debates about this, but this is what I came up with, which is that you'd have dq d tau, and this could be some sort of a space-time, and this could be a unit of time or something equivalent to. And we use, and I then would say, if you would have this, you would have used infinite quantum statistics, and we have q's in some sense proportional to length less than or equal to Planck length. You have a very astonishing conclusion, which equation 8 would probably be biased toward a low non-zero entropy count, which would mean for finite initial entropy connection information transfer, we'd had through equation 8 and equation 9 a very low but non-zero initial entropy, and that is what one of the things, as I said. Comparing the inputs of equation 5, 6, 8, and 9 against force against individual gravitons in a pre-Planckian spacetime. The reason I came up with this number 4 is because I had a discussion with the creator of with Steinhardt. And I had a long discussion with Steinhardt in 2012. And this was actually before in Paris. And he said, could some form or some type of a graviton exist to say in the pre-universe, or could you have something like that could exist? He said at the question. And so then what I said is that if you would have initial gravitons that might exist conceivably, or something corresponding to them in the pre-Planckian spacetime up to Planckian, which sounds incredible And that was Dr. Steinhardt's question. He was, you know, he was the ecliptic model of the universe. So I said, is that, well, what would happen if you would have what we were talking about up here with this, and what would happen if you would have this, say, initial, some sort of a force upon some sort of a pre-Planckian version of gravitons or something like that. And so then what I came up with was that, well, if you have a bubble of space-time with a very small volume, and you have a Planck time, if A initial, and here's the, you'd have a force of some sort of this, say, like quantum fluid or something else, sort of unit volume. And this is what I came up with right over here. It came with a delta E right over here. And so this is what I said, if you really wanted, and the question was generated not by me, but by my conversation with Dr. Steinhardt, because we talked for half an hour. Could a graviton from an earlier universe survive and show up in our present universe? If so, what would be the force on it? And both Steinhardt and I just looked at each other and said, I have not the foggiest idea. This clumsy argument is a result of my conversation with Dr. Steinhardt. And I said, I give him credit about that. All right, now, which is that then, which is that, well, when we have all of this, is that still though, in the classical limit, there's what is known as a Poisson's equation. And here's what I did with respect to the Poisson's equation. And if you had something like a pre-Planckian graviton, where you might even talk about forces, this is semi-classical. And then I said, we'll use the pre-Planckian pressure and the data associated, and this is in Platon physics. And so then what I just came up with was, I said, if you had the mass of a graviton, if you had the mass of a graviton that existed, some sort of force in pre-Planckian, the Planckian spacetime, and this itself is commensurate with conditions that you'd have this initial treatment of the initial wave function. And if you would also have this treatment of the constant in terms of the, you know, like a constant behavior of the Ricci tensor. And you would have this right over here. You'd have all these conditions get wound into place. Is that you might, after with a certain type of limit, come up to say with what might be some sort of a initial condition, let's say an initial condition to say for the radius of a bubble of space-time, which is what this argument right here is about. A candidate potential functional will come next, which way of attain a critical value for R is given by 14. And here's the pre-Planckian. So I said, well, you're going to put that in. And this is something which I worked out with people in the Ukraine. And it had to do with a pre-Planckian treatment of a generalized uncertainty principle. This is in the pre-Planckian condition, what I said, the pre-Planckian condition was roughly equivalent to a shift in energy, H bar, and you'd have H bar of delta T, and you have H bar over A squared min over phi n, and the n referred to an inflaton that you might get in initial pre-Planckian conditions. And so, well, at the end of the day, which is that what would this have to do? This is comparing the results of non-zero delta B3, and delta B3 is referring to a early space-time volume, pre-Planckian to Planckian, to say you have a non-singular beginning of the universe. And so then what I said, well, go back to this equation before that we were talking about, and we already have right up here about the initial condition. Let me just go back to what it was. The initial condition has to do with something that's looking like a semi-classical action, which you have something like that. is that we could reinterpret then what was being done with respect to the wave function to come up, which you might call Bohmian type of mechanics. I'm not saying it'd be Bohmian quantum statistics or something else of sort. And well, then, which is that that's just you want to put in, you know, what I did with respect to the action or things. So this is another way of saying this is another way of at least parceling it. And the conclusion, overlap with Bohmian quantum picture physics equation 4 is confirmed for pre-Planckian spacetime. And that is right over here, is that this would be for the action, other things of sort would be small but non-zero. You want to have something that's small but non-zero, and this would be connected with what I was doing right over here at the initial space-time, and also connected with what you might call this choice of the Ricci tensor. And the starting point for all this is looking at this type of a functional right over in here. So that's what I said, is that you could just do that. So, which is that at the end of the day, this action and everything sort wouldn't be zero, but it's small. You're saying it doesn't, you're saying is that there would be perhaps a radius of space-time, which I'm referring to right over here, a radius of space-time initially, which is non-zero, but which is very, very small, in which then you could go to a Bohmian type of treatment, let's say, of initial conditions, and I just say what they are. And here's a so-called quantum potential, and I put that in, and that was what I was able to get. Now, which is that the question to raise in all this, though, is, let me go to what the, okay, this right over here has something which I worked out and confirmed before I turned the damn article in. I did the derivation of this. What is the point, a question that a person can legitimately raise? Phi itself really isn't an issue, all right? The question is that if we have something like a pre-Planckian to Planckian bubble, and we're talking about this RCA, RRR, how legitimate is this, and how much can we come up with? And here we have this K. This has to do with the curvature, you know, which is, we're saying, wow, this thing has a lot of curvature to it. But I was saying at the beginning, assume is the curvature something else right at the bubble of space-time would still be a constant. So that is my talk. And I am now leaving the door open to questions from the audience.
Okay, thank you.
Now, I'm very hearing impaired, so you're going to have to speak up.
Yes,
it's not you,
thank
it's
you
my
for
deafness.
thank you for your presentation. And now it's, so we have a large amount of time for questions, comments, and discussion. So if anybody has some question or comment, please speak up.
I'll tell you what my biggest comment is. You know what my biggest comment is? What you want to, I'm going to show you the thing that bothers me, which I don't have an answer for. Let me show you what it is. Let me go right up to the top, right over here. What bothers me? Okay. Okay, aside from this crazy point, which I put in from because of Steinhardt, what's been getting on my case? This thing. Okay, because I'm saying at the boundary of space-time. Let me tell you what this is. At the boundary of, here's my question, which I want to ask you, and I really mean it. I'm saying this thing is a constant. You can put in, okay, great. Here we have a curvature. We have an initial third thing. Sorry. Let's say this is like 10 to the minus 25. This is a big number. And we have some sort of, and we have curvature or something like that, right at the bubble of space-time. What is meant by curvature or something like that when you're right at the bubble of space-time right when you start to nucleate space-time? I don't have an answer to that. I'm asking you.
Okay, thank you. So we have this.
It really this is what really bothers me the most. Yes. Okay, I'm showing you right here.
Okay, thank you. So we have also now a specific point. If maybe anybody has a comment, please type in the chat or unmute yourself and ask. I will wait.
I don't know what it means to have curvature right at the bubble of space-time. Let's say if you went to loop quantum gravity. Let's say if you go to loop quantum gravity, all right? Loop quantum gravity, and you talk about some sort of a space-time bubble, okay, or something like that. How do you define curvature at the surface of a loop quantum gravity, so-called bubble of non-singular space-time? I don't know. I put it in because it seems to be consistent, but I don't know.
It's not an easy answer to have. Okay, maybe this, I have a couple of very, very simple questions because I'm not familiar with the original equation. So if you could go at the very beginning of your talk, when you introduce the starting equation, the fourth order equation from which you started with, could you show that again, please? And maybe you could explain a little bit more since we have still a little bit of time.
Well, I can, as a matter of fact, I can say something about that right here.
Yes, and how it's coming out and what properties, what known properties, what are the known properties?
Well, there's a beautiful argument that was done in a book on quantum gravity by Kleinst.
Sorry, at the moment I still see equation 6. Did you move up with the?
This is the thing that bothers me the most, right here.
Yes, I understand, but my question was about the starting equations, the one from which you started your talk, just to understand how this equation, the starting point, is motivated.
Well, what I did, well, this right over here, what I did right over here was I went straight over to Wheeler's book, and I just cribbed something straight from Wheeler's book, you know, that had to do with was a Schwarzschild type of metric, and I used something very similar to that. And so this is something which I just cribbed directly from Wheeler, but then I put some other terms in there because Wheeler wasn't necessarily concerned to say was curvature or something else. So I said, well, what if you have something like curvature and other things of sort? So this RCA or this RCC or something like that, which I would pick, is something which I took straight from the 1971 book on gravitation.
Yes.
I'm telling you where it came from, the basic idea.
Yes, this, okay, this I understand about equation 6. How about equation 3 or 4? I don't remember.
Want me to go to the equation 3 or 4?
Yes.
Sure, I'll do that.
This is clear. I understand your point.
Oh, no, no problem.
I would like to know a little bit more about this starting point, equation 3, and how we go from 3 to 4, for example. So, for example, I expect the psi to be a function of R and
T. I'm going to have to put in a big fat one-page derivation of this in the conference proceedings.
No, okay. So, for example, psi is a function of R of spatial coordinates, but also of time in the 3, right? So I'm expecting these A and B, they are 0, 1, 2, 3, or so they are space-time indexes.
Well, a lot of stuff drops out, as you assume, example, if this thing right over here is relatively a constant or something like that, or very slowly varying, lots of stuff drops out. If you don't make that assumption, it's hopeless.
So the psi is in 4 is only a function of R, or it's still a function?
It's only a function over R in this situation.
Okay.
What I'm assuming, let me explain. I didn't say this explicitly, but it's a very good question. What I'm saying is that we don't have a notion of time in the boundary between the pre-Planckian and the Planckian. You know, I removed the time variable for very much the same reason that, you know, was done in the Wheeler-DeWitt in the equation of the universe.
Yes.
And the idea was, how are you going to define time? How are you going to define time? Okay, when you don't even have an arrow of time. You don't have an arrow of time. You don't have anything. You just simply have initial conditions. You might have something spatially, something like that, that's configured in an emergent configuration, but that's it.
Okay, thank you. And I have
so
another
I'm
question.
saying the thing which was that, but so what I'm saying is that the reason why this had an R dependence of the thing was because I was saying you really don't have time configuration right in the being. You just have an emergent phenomena.
Okay, thank you.
All right, so that's what I was assuming.
Yes,
but
and I have another question, sorry, about
that has been this.
Sorry, and I have another question about that equation. So is there any limit, the starting point, like the higher order equation, is there any limit in which that equation becomes just Wheeler-DeWitt? So is it a generalization of Wheeler-DeWitt, like that can be reduced to Wheeler-DeWitt in some limit?
My impression is that lots of the higher order terms would just cancel out.
Okay, okay, thank you.
And I have to prove that in a paper.
Okay, thank you very much. Sorry, this was just
also an
incredibly
legitimate question. You understand what I'm saying?
Yes, I understand.
It's incredibly legitimate. I'm saying is that most of the stuff just cancels out, and going from here down, and going from this thing, which was done by Victuli, right over here, which is all sorts of things down to here. And Bob, if you don't have the existence of time itself specified, but you have other things destroyed, it's a very good approximation because things are so small at a so-called non-zero but very finite boundary. At that point, which is that lots of terms cancel and drop out. Yes. That's what happened.
Thank you.
And it's a mess. It's a messy situation. But what makes this thing fly to a certain degree, but where I have all my questions, is this thing right here. You understand what I'm saying?
Yes, I understand.
And I go back to the question. See this term right over here? How does someone define curvature at the so-called bubble of space-time? You know, like a non-zero bubble of space-time. But you have curvature at the surface, and you're not even really to the point. You're just talking about an emergent structure. Well, I'm going to have to really have a good answer for that one. I'm asking you because to me, it's not clear yet. The idea in one sense is very clear, but what to do with it is not clear. You understand what I'm saying? Go back to loop quantum gravity. Does someone have curvature at the surface of the bubble of space-time? Well, maybe yes. What is it? How do you define this? This, you know, like this, they have these signs and everything. So I'm not assuming that you'd have like k equals -1 + 1 or 0. I'm saying that this is, you know, you have some sort of curvature structure, which is there, which you're going to have to define at the surface of a bubble. And if I get that straight, I might be able to say something intelligent about the rest of the problem. You understand what I'm trying to say to you?
Yes, kind of. I'm not sure if I get everything, but the main point, I think,
but
the main difficulty that you have is clear.
Terms, yeah, but lots of terms from 3 to 4 drop out because you no longer are having to work, and then Vitili did some of this too, because you're no longer assuming to say a direct time variable. Time is not considered from the pre-Planckian to Planckian. We're talking about a purely emergent phenomena. In other words, in here, this really, you know, that's what the problem is. Do you understand what I'm saying? Roughly.
Yes, I understand the main idea, but I'm missing some technical aspects. But maybe we can.
Okay, well,
we can see.
Anyway,
maybe I can read
give me a lot of
the,
ideas of what I'm going to have to write up in terms of a conference proceedings.
Yes.
I'm going to
and
have
also some references to check some references would be useful.
Yeah, otherwise it said you could go shoot me and not publish it.
Okay.
So anyway, I want to thank all you gentlemen for listening to me. I thank you. God bless you.
Thank you for your presentations, which
yeah, well,
require to deal with very fundamental.
Try to simplify it
with very fundamental questions. So okay, so thank you again for both talks.
Yeah, well, I'm also saying the other part was it about that. Why I even brought up gravitons or something like that, or something equivalent to that, was because of a discussion I had with Dr. Steinhardt, and it was in Paris. And so we're sitting around talking about what would happen if you had a graviton from a prior universe shows up and somehow gets transitioned over to our present universe. What's going to happen in that situation? We're talking about for half an hour. At the end of the day, we don't know.
Yeah, I think
so I just put my guess.
I think this is the kind of question that you should first understand the question, and then you can try to think of an answer. Yes, because it's not obviously clear, of course, what this can mean, and so it's very very challenging.
Which is the person who answers that fully should get the Nobel Prize.
Okay. Okay, well, that's not up to us, but
at least I think the question's interesting.
Yeah. Okay, so thank you very much again.
Thank you very much. Thank you. I really appreciate it, Stefano. Thank you for your gracious hosting me in this session. Thank you.
Thank you.
And Ashu, I just want to thank you very much for your presentation. I didn't want to muck it up with my dumb questions. I can ask some really stupid questions.
Okay, so thank you again. So the next speaker.
Okay, God bless all of you, and you have a good. God bless all of you, and you have a good session. And I hope that you're happy with the conference. Thank you very much.
Thank you very much. Thank you.
You're welcome.
Okay, so we are on schedule, I think. So now it's basically 11:20. So we have this 5 minutes of technical break. So I would like to ask Peter if he can already start sharing, and whenever he finds more appropriate, he can start his presentation. So the next talk, which is supposed to start at 11:25, has titled General Relativistic Evolution Equations for Density Perturbations in Friedman, Lemaitre, Robertson, Walker universe, and the problem of structure formation. So as for the previous talks, we are a little bit early. So Peter, if you would like to wait for 11:25 so that your talk will start at the
yeah, that's fine. That's fine.
At the scheduled time, and somebody may join. Otherwise, you can feel free to start anytime. And we may have more time for questions and answers and discussion after the talk. Thank you.
Okay. May I record myself my talk, or is that not?
Okay. So. Of course, I don't know how you can do that, but if you know how to, please do that.
Well, please ask the host to give you permission to record.
Then I don't know if I can give you this permission,
okay.
But if you send me an email after the session or after the meeting, I will make sure with the organizer that maybe you can have some way a video of your presentation, so that you don't have now to bother with the registration, but you will have it in some way.
Okay, thank you.
Okay. So if you can, when you are okay, please start sharing your screen and.
Yeah. Okay. Share screen. Oh, I don't see your. I've only your desktop. Speaker view, gallery view. No, that's not it. speaker view.
So you click at share screen and you may have some options after that.
Yes, but I only see you.
Share screen, did you select the window like whiteboard, iPhone?
There it is. There it is. Desktop 1, share screen. Do you see it?
Not yet.
Not yet. And my video is also not start my video. That's my video. Yeah, of course. So now share screen. Yes.
Perfect.
Perfect.
If you can go full screen, now we are ready.
Okay, full screen. Present slideshow.
Yes, perfect.
Also?
Very good.
Okay.
Thank you.
Can I start off now?
Yes, sure, you can start.
Okay. Well, I am Pieter Miedema from Breda, the Netherlands. In this talk, I will explain how to solve the gauge problem of cosmology and how I derived a new cosmological perturbation theory for the Friedmann, Lemaitre, Robertson, Walker universes. The new theory provides a possible solution to the problem of structure formation in our universe. Well, the outline of my talk is as follows. First, I will explain the gauge problem of cosmology and how to solve it. Next, I will show how to derive the new perturbation theory, which has the correct Newtonian limit in an expanding universe. And finally, the new perturbation theory will be applied to a flat universe in the radiation-dominated era and the era after decoupling of matter and radiation. But first, the gauge problem of cosmology. We consider a universe filled with a perfect fluid with a non-barotropic equation of state. Only if the pressure depends on the energy density and the particle number density, a density perturbation may exchange heat with its environment, which may possibly enhance its growth. Well, then the background equations for the universe give the global evolution of the universe, and the linearized Einstein equations give the local evolutions of the diabatic or non-adiabatic density perturbations, and possibly the growth of structure in the universe. It is well known that the general theory of relativity is invariant under general coordinate transformations, and therefore the linearized Einstein equations and conservation laws are invariant under general linear coordinate transformations. So there is general covariance, so there are no preferred systems of reference. One may choose any coordinate system that makes the calculation easy. However, linearity of the perturbation equations creates the problem of creates the gauge problem of cosmology, which must be solved first. Well, the universe is characterized by three scalars. First, the expansion scalar, the energy density, the particle number density. The perturbations to these three scalars transform under a gauge transformation according to where S is one of the three scalars. Now, the gauge problem of cosmology is if S1 is a solution, then S accent 1, dus the transformed quantity, is also a solution. Well, the solution contains the gauge modes, so therefore S1 has no physical significance. And the conclusion must be that the perturbations to the three scalars of the universe have no physical significance. The gauge problem dates back to 1946, when Lifshitz for the first time formulated the perturbation theory for a flat universe. Since that time, there is an extensive literature to address this issue. All researchers agree that quantities that describe physical phenomena should be independent of the choice of a system of reference. However, there is no agreement on which gauge invariant quantities are the true energy density perturbation and the particle number density perturbation. None of the cosmological perturbation theories in the literature has the correct non-relativistic limit. So the interpretation of the gauge invariant quantities is difficult. So there is still no solution of the gauge problem of cosmology, and structure formation in the early universe cannot be explained using the perturbation theories in the literature. And this was my very motivation to try to develop a new perturbation theory which has the correct non-relativistic limit, as I will show in the following slides. The solution to the gauge problem. Well, what we know for sure. The three gauge invariant, the three quantities which describe physical phenomena should be gauge invariant. The Einstein equations and conservation laws describe physical phenomena, and therefore the physical quantities should be some linear combination of the solutions such that the gauge mode disappears. Gravitation is already weak in a linear perturbation theory, so that the non-relativistic limit can be attained by taking the limit that the local spatial fluid velocity are small with respect to the speed of light. Furthermore, the relativistic gauge transformation must become equal to the Newtonian gauge transformation, where time and space are decoupled. And the gauge problem of cosmology can now be formulated as find linear combinations for the three quantities. Well, the perturbation to the three scalars of the universe transform under a linear transformation in exactly the same way. Therefore, we can combine two of these quantities such that the gauge modes are eliminated. And then we have three choices. The obvious non-trivial choice are the formulas in the box. The gauge invariant perturbation to the global space, to the global expansion of the universe vanishes, and therefore density perturbations have no influence on the expansions. Are the quantities in the box the real physical perturbations? Well, to find out, we have to take the non-relativistic limit. But first, we have to rewrite the linearized Einstein equations and conservation laws into a more convenient form. Well, there is general covariance, and therefore we use synchronous coordinates for the following two reasons. In the Newtonian gravity, all coordinates are synchronous, and that facilitates the taking of the non-relativistic limit. More important, in synchronous coordinates, we can use the decomposition theorems for symmetric tensors of rank 2 of three spaces of constant time. The perturbed metric and Ricci tensor are decomposed in scalar, vector, and tensor perturbations. The perturbed metric for scalar perturbations can be written as a linear combination of two independent potentials. Well, the first potential becomes the Newtonian potential in the non-relativistic limit. The decomposition of the Ricci tensor and the particular form of the second potential are needed to make the decomposition of the spatial fluid velocity in a divergence and a rotational part compatible with the three momentum constraint equations. The decomposition theorems imply that only scalar perturbations are coupled to density perturbations. And therefore, the general solution of the linearized Einstein equations and conservation laws is a linear combination of the scalar, vector, and tensor perturbations. And we know already that only scalar perturbations are coupled to density perturbations. And therefore, we replace in the full set of Einstein equations and conservation laws the perturbed metric, the perturbed Ricci tensor, and the local fluid velocity by their scalar counterparts. Here, R1 is the local perturbation to the global spatial curvature due to local density perturbations. The rotational part of the local spatial fluid is not coupled to scalar perturbations, and therefore the three components of the fluid velocity can be replaced by the divergence of the fluid velocity. Now the linearized equations can be rewritten into a new system that only describes scalar perturbations. Well, the result is a set of equations that only describe scalar perturbations. Well, we have the constraint equations. The first one is an algebraic perturbed Friedmann equation. And the second, due to the decomposition theorems, the three momentum constraint equations can be rewritten into one first-order ordinary differential equation for the local perturbation to the spatial curvature of the universe. And we have, of course, three conservation laws. Now, the evolution of the gauge invariant quantities is completely determined by the background and the perturbation equations. Note that also the gauge modes are solutions of the evolution equations for scalar perturbations. Now we can take the non-relativistic limit. In the Newtonian theory, free space is flat, and therefore we consider a flat universe. The Ricci scalar contains second-order spatial covariant derivatives of the metric, which reduce to ordinary derivatives in a flat universe, so that the trace of the perturbed Ricci tensor reduces to the Laplacian of the potential phi. Now we take the non-relativistic limit. Then the momentum constraint equation implies that the potential phi is time independent. The background and linearized Friedmann equation imply the Poisson equation of the Newtonian theory. The gauge invariant definition of the perturbation to the particle number density reduces to the energy-mass relation of the special theory of relativity. Finally, the relativistic gauge transformation reduces to the Newtonian gauge transformation, where time and space are decoupled. Time coordinates may be shifted and spatial coordinates may be chosen arbitrarily. The conservation laws have in the non-relativistic limits only gauge modes as solutions, and therefore need not, they can be discarded. And the conclusion is now that with the definitions are dus indeed the real physical perturbations, so that the gauge problem of cosmology is finally solved. I have already said that the evolution equations for scalar perturbations determine the evolution equations for the real physical density perturbations. However, they have also the gauge mode as solution, and therefore they are too complicated. What we would like to have is evolution equations which have only the real physical density perturbations as solutions, without the gauge modes. I have used a computer algebra system to rewrite the evolution equations for the gauge-dependent scalar perturbations to equations for the two gauge-invariant fluctuations. And the result is one second-order ordinary differential equations for the energy-density contrast function and one first-order ordinary differential equation for entropy perturbations. For barotropic equations of state, the right-hand side of this equation vanishes, and therefore a perturbation evolves only under its own gravity, and there is no heat exchange. From the equation of state and thermodynamics, it follows that in the background, the entropy is a constant. However, the perturbed density perturbations, diabatic density perturbations, do not only evolve under their own gravity, but they may also exchange heat with their environment. And we will now come to the structure formation in our universe. Well, the radiation-dominated era is characterized by the well-known relativistic equation of state for radiation, where the contribution of ordinary matter and cold dark matter to the pressure is neglected. The equations of state imply the evolution equations. These equations hold true for radiations, ordinary matter, and baryons and cold dark matter. From the entropy equations, it now follows that fluctuations, the entropy equation, that fluctuations in the cold dark matter are coupled to fluctuations in the energy density. The general solution of this equation is, and from this general solution, we see that density perturbations oscillate with an amplitude that grows proportional to the square root of time. For large-scale perturbations, we find the well-known solutions of the literature. And the conclusion must be, because cold dark matter perturbations are coupled through gravitation to perturbations in the radiation, cold dark matter perturbations do not form the seeds of structure formation after decoupling. So we now consider structure formation after decoupling of matter and radiation. The equations of state are those for a monatomic perfect fluid. The first term is the rest energy density, and the second term is the kinetic energy density. From the background evolution equations, it follows that the matter temperature decays inversely proportional to the square of the scale factor of the universe. As is well known, one may neglect the pressure in the background universe. This, however, is not allowed in the perturbed universe, since if there are no local pressure perturbations, there is no local fluid flow and therefore no structure formations. So the pressure is always non-zero. These equations of state imply the evolution equations, and the solution of the entropy equations is and that is just like the matter temperature, the difference of the fluctuations in energy density and particle number density evolve inversely proportional to the square of the scale factor. The velocities are non-relativistic, and therefore delta n is the fluctuations in the rest energy density, so that the difference delta n, delta epsilon min delta n is the fluctuation in the kinetic energy density. Now we see that the delta t is a constant of the theory, or in other words, the entropy perturbations is a constant and is also a free parameter. The evolution equations for fluctuations in the energy density and the entropy evolution equation can be combined into one equation. Note that the entropy term is of the same order of magnitude as the pressure term. Now all observable quantities are contained in one parameter mu, m, the present value of the Hubble parameter, the redshift as decoupling, and the present value of the background radiation temperature, and the mass, the proton mass m. The evolution of density perturbations depends on the scale in parsec and the initial entropy just after decoupling. For large scales, heat exchange is nearly impossible, so that the well-known solutions of the literature are found. In order to solve this equation, we need initial values. Well, the initial value from the Planck collaboration, this value is far too small to explain structure formation with the standard perturbation theory. And that's why cold dark matter has to be invoked in the standard perturbation theory. That is not needed in the new theory. The initial growth rate is unknown, and therefore I take no growth at all. The only assumption I make is that the entropy perturbation takes on random values. If perturbations go in a very short time from a very high pressure era to a very low pressure era, then some small eras end up with positive entropy perturbations and others with negative entropy perturbations. The positive values give large voids, and the negative give possible structure formation. The results of the integration of the evolution equations are given in the next graph, and the curves are labeled by the diabatic pressure perturbation delta t. The perturbations start to grow at the time of decoupling at this z. Each curve shows the time or the redshift when a perturbation becomes nonlinear, that is when delta epsilon equals 1. On each curve, delta epsilon equals 1. The growth is governed by internal gravity and heat exchange. At a scale of 6.5 parsec, gravity and heat exchange work perfectly together, resulting in very early star formation. because of the steepness of the curves to the left of this peak. I call this value the relativistic gene scale. For scales larger than the gene scale, gravity is strong, but heat exchange is low because of its large scale, resulting in a later collapse time. The larger the scale, the later the collapse. For scales smaller than the gene scale, gravity becomes rapidly very weak because of the small scale, resulting also in a much later collapse time. The next graph shows the growth rates of a density perturbation as function of its initial scale after decoupling. Now, the fastest growth occurs within the first 16 million of years. Density perturbations at the gene scale, 6.5 parsec, grow fast until non-linearity. Perturbations of scales 4.1 parsec grow initially faster than perturbations at the relativistic gene scale. Eventually, the rapid growth slows down, and the perturbation grows slowly into the nonlinear phase. Perturbations which are smaller than 4.1 parsec oscillate towards nonlinearity. Perturbations smaller than approximately 2 parsec or larger than 50 parsec do not become nonlinear within the age of the universe. Now I come to the summary of my results. I have derived a new, first a theory. I have derived a new cosmological perturbation theory with the following properties. It has a Newtonian limit in an expanding universe, and therefore the gauge problem of cosmology is solved. I have found a second-order evolution equation for the true physical density fluctuations and a first-order evolution equation for entropy perturbations. Local density perturbations do not affect the global expansion of the universe. Application to the flat FLB universe. First, radiation-dominated universe. I have found that delta, these fluctuations, oscillate with an amplitude proportional to the square root of time. The well-known relation follows from the general theory of relativity, and therefore it holds true for all kinds of particles that interact through gravity, and in particular cold dark matter. And therefore structure formation can start only after decoupling. For the universe after decoupling, structure formation depends on both the initial value of the entropy perturbation and the initial scale of a density perturbation. I've made only one assumption, that the initial entropy is a random value. The relativistic gene scale is found to be 6.5 parsec, and the relativistic gene's mass is about 4,300 solar masses. And the first stars occur rather early in the universe. Well, I've shown that the general relativistic perturbation theory for a flat FLAW universe explains structure formation in the early universe without the need of cold dark matter. All details of the perturbation theory and its consequences can be found in these two articles, and you may contact me through Twitter or email. Thank you for your attention.
Thank you very much, also for fitting well within the time. In fact, you had basically another 5 minutes.
Okay, thank you.
But thank you. So now it's so we can have a slightly extended question and discussion session, and therefore I would like first to ask if anybody present has any question or any comment or
Can I? Hello?
Yeah.
Yes.
Thank you. Just a little curiosity, when you say that you assume a random value for the entropy, since we have some time, can you go a bit further and explain what you mean with the random and how you do actually do that? Thank you.
Well, the random value is in the oh, sorry, is in the source term. Well, this value cannot be determined. Oh, so yeah, it could be any value, and I've taken as the largest value minus 0.1, and I assume, well, this is my assumption, that the initial value of the entropy perturbation is some random value and depends on how a perturbation undergoes a very fast transition from the very high pressure epoch just before decoupling and to a very low pressure after decoupling. So that can then you can have some variation in it. Well, it's an assumption. I don't know if it is true, but if that is not true, then there are no structure. Then there is no structure in the universe.
Okay, thank you.
No.
Thank you for the question and also for the answer. Is there any other question or comment?
I have also a question for me.
Yes, please.
So it's regarding your claim that perturbations do not affect the background expansion of the universe. I was wondering if this is a result only at, let's say, at the first orders in perturbation theory, or you think this can be a general consequence for all kinds of inhomogeneities, and if so, can you comment something on the back reaction program?
Yeah, well, it is a first order perturbation theory. The back reaction, well, in my opinion, there is no back reaction. Oh, where are the formulas? In my case, if you choose these definitions, dus epsilon vis and n vis not equal to 0, then you have automatically that theta 1 vis is 0, and it follows from these transformation rules. You can also choose another one. You can choose epsilon 1 vis equal to 0, and then this one is not 0. But that is not real, I think.
You think you can make this choice at maybe other orders of perturbation?
Well, I have made this choice because in the... Oh, even kijken. I have made this choice because... Yes. Well, there are no other quantities. So I have only epsilon 1, n1, and theta 1 as scalars in the background. So I have no other choice than these definitions.
Okay, thank you.
So sorry, does this answer? So there was the question was probably asking if this can be maintained at higher order in perturbation theories. If there is, I mean, if you have any clue about this, I understand that the higher order is more complicated.
No, I've not researched it in higher order systems. Okay. Maybe that in higher order perturbations, it could go different, of course. But you have to start with first order.
Yes, yes, of course.
Okay.
Thank you for the question again, and also for the answer. So we still have some time for other questions, or comments, if anybody has questions or comments. Well, if not, then let's thanks Peter again. Thank you for the talk and for participating in the session. We still have one talk, which in our schedule was planned for 12 o'clock. Let me check. Yes. So again, I think the speaker Jorens can decide how he prefers. I mean, if he is okay with waiting 10 minutes and start at the scheduled time, we can, well, 8 minutes now, and start at the scheduled time, this is okay. Otherwise, we can maybe start early and have a little bit more time for question and discussion, or end the session early, which would be, I think, something usually unseen. Okay. So early universe, early ending, and if we make also the early proceedings, then we are basically like a very, very out of 5 sigma case, I think, in the parallel session world. So thank you again.
Okay, yes, thank you very much.
Thank you.
So stop sharing now?
Yes, you can stop sharing. Thank you.
So.
Thank you very much.
Then I shall mute myself.
Thank you. And maybe we can already share the next screen. And please feel free to start whenever it's appropriate for you.
I think I can start already. And
yes,
it's fine if we finish a bit earlier, I guess.
Yes, I think I don't know. It's for me as I think for some of you the first time that I see the Marcel Grossman online. So it's difficult for me to understand how much people are planning to jump from one session to the other. I know that when it was physically, this sometimes happened, and sometimes people were rushing through big universities, big campuses.
People going out and
sometimes to give the presentation, sometimes to listen to others' presentations. But I think that nowadays, I mean, since we are all used to this Zoom or whatever, I mean, Teams or Skype and recording, I am also expecting that many people will maybe look at the talk later. So I don't expect.
I think so too. It's also easy to just check whatever talks you're interested in and watch the recordings, especially if there is some kind of overlap.
And there is no risk to lose everything by trying to jump across inconsistent schedules.
Exactly.
Okay, so very well. So please start. So the next talk is about entropy and irreversible processes. We'll focus, of course, in gravity and cosmology. Thank you.
Okay, thank you very much for the introduction and the opportunity to present my work. As you said, this work is on entropy and irreversible processes in gravity and cosmology, part of my PhD thesis done in Madrid at the Instituto de Física Teórica, and done in collaboration with my PhD supervisor, Juan García Bellido. And the main idea of this work, and what I will try to convince you about today, is that we need to incorporate irreversible processes into gravity and into any metric that we derive from it in a consistent way. And this is not done in principle in general relativity, but can be incorporated, as I will show you. So why is it not moving? No. So this is the outline of my talk today. We'll start with a brief motivation of why we're doing this. Then since this is the early universe session, I will give a focus in cosmology. And so before talking about irreversible cosmology, I will first very briefly talk about what I mean by reversible cosmology. Then, in order to introduce irreversible processes, I will talk of entropic forces and what is the proper mathematical formalism to incorporate them into some variational formalism of any physical system. First in mechanics as a toy model and as work that was already done by others some time ago. Then I will apply this to general relativity, and I will show you how this works. Once we have understood how this is incorporated into general relativity, I will apply it to a particular case of cosmology and how to obtain so-called non-equilibrium cosmology. Then I will give an idea to obtain cosmic acceleration from this, and I will finish with some conclusions to wrap up. So the motivation, as you all well know, general relativity is a time reversible theory, and as any theory that comes from a Lagrangian or comes from an action and is formulated in variational terms, in this case with the Einstein-Hilbert action, this is usually a symmetry that comes with the theory. Now, what we see in practice, for instance, in cosmology, is that most of the universe expansion history is adiabatic. But nevertheless, there are a few non-equilibrium epochs. And if there are a few non-equilibrium epochs, this means that there is some notion of time irreversibility and some notion of arrow of time that we should take into account. And like I said before, irreversible phenomena are not included in general relativity in a complete and systematic way because it is a time reversible theory. And so we will try to do this. I will try to how to do this in the talk. So also as motivation, reversible cosmology, what I mean by reversible cosmology is the most basic homogeneous and isotropic universe that is described by a highly symmetric line element that you see there, the Freeman-Robertson-Walker universe. It's filled with a perfect fluid that is characterized by a stress energy tensor that depends only on some density rho and some pressure p that are usually functions of the scale factor. And once we take these ansatz for the metric and we take this perfect fluid and we find the dynamics of this using the Einstein equations, we get the Freeman equations that simply rule the time evolution of the scale factor of the universe. Nothing new here. Now, what can we say about this perfect fluid? As you all well know, because of the Bianchi identities, it satisfies covariant energy conservation. And this means that the following continuity equation for the density rho and the pressure P is satisfied. But you can also obtain this continuity equation in an alternative way. It can also arise from the second law of thermodynamics. If you consider the product of the temperature times the time derivative of the entropy, you get that the change in this quantity is equal to the change in internal energy plus the work done by the expansion. And if you set this quantity to 0, that is, you assume that thermodynamical equilibrium has been is true for the expansion of the universe, then you get precisely this continuity equation. But in general, we could think of fluids that fill the universe and satisfy and can be out of equilibrium, and more generally satisfy that T times the derivative of the entropy is greater or equal than 0. So should we go beyond adiabatic cosmology? It doesn't seem that we have much choice coming from the Bianchi identities, but okay, we can try. We can postulate this continuity equation. And if we add this term, this non-vanishing term of the temperature times the derivative of the entropy, and we combine this with the first Freeman equation, that is, we take the first Freeman equation which has the density in the right-hand side, we time derive it, and from this we get a new version of the second Freeman equation, which has this additional term at this last term in the right-hand side, which depends on the variation of the entropy, and is therefore a non-equilibrium term that delivers a non-equilibrium second Freeman equation. Like I said, this is not what we get from Einstein field equations. So there's some way around this. Well, we'll try to make this previous statement more rigorous from the mathematical point of view. And in order to do so, I will apply what is called the variational formulation of non-equilibrium thermodynamics. This was developed some years ago. And it's basically the synthesis of two physical principles, which is the stationary action principle and the laws of thermodynamics. The stationary action principle takes an action, a Lagrangian, and so defines the physical problem. And it's a physical problem defined in variational terms. So we have this action, and we take the variation of it, and we say that when this variation is equal to 0, we get the physical solution to the system we are trying to describe. But now we want to incorporate the laws of thermodynamics to this. We can do so by imposing some constraints. That is, we are imposing variational constraints on the physical problem. And then when we try to find the solutions to this variational problem, we don't get the same as before because the problem has been constrained by some additional equations. And so when we solve it, we get a solution that is indeed gives a stationary reaction, but also has but also fulfills the constraints that we have imposed before, and that are the laws of thermodynamics. And I will show you this more concretely how it works. Indeed, let us consider a mechanical system. This mechanical system is described by an action that is a time integral of the Lagrangian. And this mechanical system has simply 2 degrees of freedom. There's some physical variable q or coordinate q, time derivative. And then it also has an additional degree of freedom but that we usually don't encounter in mechanics, which is the entropy, which we consider as an independent degree of freedom from the coordinate q. Now, when we take the variation of this, we get the usual variation of the action times some variation coming from the variation of the entropy. And now we can turn this into a variation of the coordinate by adding this constraint, and which relays the derivative of the Lagrangian with respect to the entropy times the variation of the entropy with some function times a variation of the coordinate. And once this constraint is incorporated, what we get is a constrained equation of motion, which, as you see, looks very much like the usual Euler-Lagrange equation, except it has an additional term, which is what we call a frictional entropic force. Of course, if there is no variation of the entropy, you can see that F will vanish and we will recover the usual Euler-Lagrange equations. But more precisely, what is this F? And well, this F needs to be obtained from an additional constraint, the so-called phenomenological constraint. That is one constraint that does not relate variations in the abstract sense, but rather time derivatives. And we can get this by simply replacing the variations by time derivatives. And this immediately gives us a notion of what F is. We can actually obtain it. And we can also get that because the partial derivative of the Lagrangian with respect to the entropy is minus the temperature, we can also get the sign for the function F if we want the second law of thermodynamics to be satisfied, that imposes that temperature times the variation of entropy should increase. Now, this relation is usually true because the Lagrangian can be expressed as some kinetic energy minus some internal energy, and the derivative of this internal energy is precisely the temperature. Now, what we get from this is 2 things. First, the dynamics of the problem is modified, and second, because F must have a particular sign, we also get that the symmetry under time reversion is broken by this. Now it's time to apply this to general relativity and obtain how do entropic forces behave there. And so we start from the Einstein-Hilbert action of general relativity and possibly some matter term added to it. And if we take the variation of this, we see again that there appears an additional term that depends on the variation of the entropy. Once again, we can relate this variation of the entropy to a variation of the metric by adding a so-called variational constraint. And this allows us to obtain the non-equilibrium Einstein field equation, which looks very much like the usual Einstein field equation, except that it has an additional term, as we had before, that we call a friction or entropic force, because it's a term of thermodynamical origin. Now, again, what do we know about this, what we could call a friction tensor F? And we actually do not know too much about it. We know from the Bianchi identities that there should be some of, it's somehow, its covariant conservation is related to the covariant conservation of the stress energy tensor, or better said, its covariant derivative is equal to the covariant derivative of the stress energy tensor. So there can be an exchange between the two, but we don't know much more so far. And in order to postulate a phenomenological constraint as we did before, we require a proper notion of time evolution. And this proper notion of time evolution and general relativity is obtained in the so-called ADM formalism developed by Arnold Deser and Misner in the 50s. As I was saying, this formalism provides a proper notion of time evolution because it allows one to formulate the initial value problem of general relativity. That is, giving some physical quantities and its derivatives at a given time, you can obtain the proper time evolution of this system and effectively some dynamics. This works as you are aware of. One performs a 3+1 splitting of space-time into constant time hypersurfaces sigma. And then one splits the metric G of the full space-time into two parts. One which we call H and is the induced metric on the hypersurfaces, and another which is simply by the tensor product of the normal vector to the hypersurfaces. Equivalently, one can write the line element as you see as a function of this metric H, and some additional functions which are the lapse function, that is n, and the shift functions which are the n, which is the ni vector. In this formalism, the Einstein field equation is equivalent to the Hamilton evolution equations. And this comes as follows. One defines one considers the metric H as a true physical quantity and defines the canonical conjugate momentum to this metric, to this physical degree of freedom as usual, as a derivative over with respect to its time derivative. And one immediately can build the Hamiltonian of this field theory as it is shown there. Now in this formalism, if once we obtain the evolution equations, the first one stays the same as in usual general relativity, but the second one, this variation of the Hamiltonian with respect to the metric, as you can see, gets an additional term, which is also a term of entropic origin and depends on this F tilde, which is the projection of the friction tensor that we introduced before in the Einstein field equations. This is its projection onto the spatial hypersurfaces sigma. And from this one also gets, to complete the Hamilton formulation, some constraints given by the derivatives of the Hamiltonian with respect to the lapse and the shift functions. Now we can already say something about this friction tensor, or better said, this spatial projection of the friction tensor. That is, we can introduce phenomenological constraints, and we need to introduce two of them, because now the entropy can more generally be a function of not only time but also space. The first one of these constraints is the so-called internal entropy production, which is nothing but relating the lead derivative of the entropy density along n, that is along the perpendicular vector to the hypersurfaces, to some lead derivative of the metric of the physical degree of freedom. Additionally, because there is also a dependency on space, we need to consider the entropy balance equation. That is this internal production of entropy, this lead derivative of S needs to be equal to the total entropy production minus the fluxes of entropy, because the fluxes of entropies are not necessarily related to friction. It can be because of matter transport of whatever, and they are not the origin of an entropic force necessarily. Now let us see what is the effect on a verifiable setup. In order to do so, we consider congruence of geodesics. This congruence of geodesics, as I said, geodesics, they don't really need to be geodesics. Let's say a congruence of world lines. And this is characterized by this tensor theta, which is the covariant derivative of n, the normal vector to this, or the vector, the tangent vector to these world lines. If we take the lead derivative of the trace of this tensor that characterizes the congruence, we obtain the Right-Chaudhuri equation that describes it. And as you know, the Ricciarduri equation is key to understand many physical phenomena in general relativity. And for instance, once one imposes the strong energy condition, in the usual setup, we get all these consequences for the gravitational collapse developed in the Penrose theorems and so on. But here, if we have an entropic force, what we see is that actually, even if the strong energy condition is satisfied, as you can see in the last equation, collapse can be avoided by entropic forces if they are strong enough and if they have the right sign. This is relevant for gravitational collapse. This can be relevant also for the dynamics of the universe. Now, how we define temperature and entropy from the matter content? This can be done very easily with analogy from a mechanical system. In a mechanical system, as I mentioned earlier, we have a Lagrangian that is equal to the kinetic energy minus some internal energy. And we read right away that the derivative of the Lagrangian with respect to the entropy is related to the temperature. And one can do something very similar with hydrodynamical matter. And for instance, in the universe filled by some fluid, one can define the temperature in a continuous and very analogous way. But one can also assign temperature and entropy to the gravity sector. And in order to do so, let's consider some horizon with some induced metric on it. And let us consider the boundary term of the action on that horizon. And we can do so, for instance, for a Schwarzschild black hole. And if you compute this boundary term, this Gibbons-Hawking-York term of the action, what you see is that this is actually equal to the integral of the mass. And so it is also equal to the integral of the temperature of the black hole times the entropy of the black hole. This, of course, it's a classical effect because the product of temperature and entropy doesn't carry h bar, but because temperature and entropy separately do carry h bar, we can argue that the appearance of thermodynamical effects from this horizon is somehow an emergent quantity from an underlying quantum description. And we can take into account this entropy into our formulation of non-equilibrium thermodynamics in general relativity. Now, let me go back to what I was talking at the beginning of my talk, namely non-equilibrium cosmology. If we apply this formalism to an homogeneous and isotropic universe, and we fill it with a fluid whose density and pressure can also have a dependency on the entropy, we obtain a Hamilton constraint that is equal to the usual first Freeman equation. And we also get the Hamilton equation, which is equal to the second Freeman equation, with this additional term of entropic origin, which depends on F tilde, which is the spatial trace of the friction tensor. And once we obtain this friction tensor or trace of the friction tensor from the phenomenological constraint, we see that we get precisely the non-equilibrium second Freeman equation that we postulated at the beginning of the talk, because it has this additional term of entropic energy. Now we can think, even though most of the expansion history of the universe are adiabatic, we can think of several phenomena which are actually out of equilibrium. This can be preheating, this can be certain kinds of phase transitions, this can be black hole formation or other kind of structure formation. This, in our framework, will lead in general to some kind of cosmic acceleration because of the sign that is given by the phenomenological constraint related to the second law of thermodynamics. And even if it lasts for a short period of time, it has a non-negligible effect. And what I argue is that it should be taken into account, and all these phenomena should somehow be revisited in light of the non-equilibrium dynamics. Now I want to give you a particular example on how the entropy of the causal horizon today may explain the cosmic acceleration that we see, that is the dark energy. If we take the causal horizon and we consider what is the boundary term in the action, and we perform the computations I showed you before, what one gets is that this term introduces an entropic fluid given by some effective density, which is somehow related to curvature in the sense that it is related with the deviation of the density parameter from 1. This entropic fluid satisfies the non-equilibrium continuity equation. And once it is taken into account in the second Freeman equation, what we see is that besides the terms given by matter, the usual curvature term, we get an additional term. It is also somewhat related to curvature, but is of entropic origin. And if we compute what is the solution to this Freeman equation, what we actually, you can see in this plot, the comparison between the usual lambda CDM model and what we call the general relativistic entropic acceleration. And as you can see, a high redshift, they both have the same behavior. And this is because the density of the entropic fluid is highly suppressed. But then close to present time at scale factor equals 1, or better said, the ratio between the scale factor and the present scale factor is closer to 1. Both models have a similar behavior. And even more, as you can see, our model may allow us to have a slightly higher Hubble parameter, and so explain the current H0 tension, possibly. And also you can see that the late time behaviors are very differently, because lambda CDM tends somehow to the Sitter universe, while general relativistic entropic acceleration will tend somewhat to a Minkowski spacetime. Now, as a final plot, we also computed as what is the equation of state of this effective entropic fluid. And you can see that it's very close to W equals -1, which is what we would expect from dark energy, from a cosmological constant. And this is currently in agreement with cosmological observations. And we hope that in the future, maybe future observations can allow us to constrain the validity of this theory. Now, let me finish with some conclusions. First, the laws of thermodynamics modify the dynamics of any physical system and break time reversibility. This is an inevitable consequence for any physical system once you impose as a constraint the second law of thermodynamics. In particular, both the Lagrangian and Hamiltonian formulations of GR can be modified in order to incorporate this. In particular, in cosmology, this means that there appears an additional term of entropic origin in the dynamics of the scale factor that is in the second Freeman equation. And we argue because of this that the effect of non-adiabatic phenomena in the expansion history of the universe should be revisited. And as a final computation, we argue that the entropy of the causal horizon is a good candidate to explain cosmic acceleration and the Hubble tension at present time. And so thank you very much for your attention. This is all I wanted to explain today. I'm now open to your questions if you have any.
Thank you very much. Thank you very much. Also for respecting very well the time limit. Well, I think the talk gives many interesting points that can be considered. So I would like to ask if anybody has any comments or questions. We have about 10 minutes for discussion if there is any point that will be raised. Thank you. Okay, if there is no questions from the audience, I have a couple maybe of I hope not too naive questions. The first one is it's very interesting to see a way in which we try to add a non-equilibrium, the description of equilibrium processes in what is our standard treatment of many physical situations, because yes, although maybe on the average or after some time, maybe equilibrium is actually a fate of many systems. There are many interesting phenomena which can be considered as out of equilibrium phenomena. So I wanted to ask, it seems, if I understood correctly, that in the present formulation, you found a way to modify the dynamical equations by adding, starting even from Lagrangian principle, by adding this effect with something which looks a very reasonable, also constraint condition, the inequality that you have shown some slides before. So my question is, if there is in this program any idea to try maybe to derive these terms that have this effect from some first principles. So as a result of some theoretical setup in which you don't have to add them, but you can say imagine them as deriving from some deeper theory or something like this. And in this sense, I would like to make already a second question. Also, this maybe is naive, but I was very curious because at some point in the slides you discussed, so usually this entropic term comes from changing, in your formula, from changing the matter kind of Lagrangian, right? But at some point you said in principle we could also add some entropic part to the gravitational sector, which is maybe discussed in another problems. So I was wondering, if I understand correctly, the results you have shown here, they are obtained by adding the entropic effect to the matter term. Did you consider also to add, so how this would change if you had a corresponding term also for the gravitational sector? So these are the two questions.
Okay, so regarding the derivation from let's say first principles, in a way this program already goes in that direction, because if we consider the laws of thermodynamics as physical principles, because we are imposing that whatever solutions we get, they should satisfy these principles. It is true that they are not encoded into some Lagrangian, for instance, but I don't see how you could do that, because probably your Lagrangian will have some time reversal symmetry. Maybe you could do this by using a Lagrangian that breaks it explicitly. I don't know, but I mean, it could be interesting to explore this. But in any case, I want to point out that this is already a step that goes towards a more fundamental joint description of both gravity and the laws of thermodynamics, because it's something that we impose already even before getting the equations of motion.
Okay.
And regarding your second question, well, you can always do both, actually. You can consider that either the gravitational or the matter Lagrangian have some dependency of the entropy as an additional degree of freedom. There is no, it is true that in most of the equations I consider what is the entropy that we associate to some matter Lagrangian, but in principle there is distinction in the formalism between the two. And actually, if you go before this part, discussing black holes, you could simply consider this term in the action, and it doesn't matter whether you call it gravitational or you call it matter.
Of course.
If it has some dependency on a degree of freedom that you want to treat as entropy, as some, let's say, monotonic function of time, then you can apply precisely the same formalism. And
okay. Okay, I see.
I don't know if that answers your question.
Yes, it does. Okay. Thank you. It's very clear. Okay, so maybe anybody else has some question or comments, maybe also on this that we were discussing now. Okay, if not, thank you very much for your talk and and also thanks to everybody that was present for part or for the whole session. We are 3 minutes early. Okay, so as I said, we are going to be consistent with the early in our session title. Also by terminating a few minutes before. I just remember everybody that tomorrow there will be block 2. If you are interested in some of the talks, of course, and if you're not talking in other parallel sessions at the time, the block 2 will have exactly the same schedule in terms of hours of time of the day as today's one. Tomorrow there will be another colleague who is co-chair of this session that will be chair for tomorrow's session. And okay, thank you again for all your contributions. I again invite you to prepare following the recommendation from the organizing committee, but to prepare also the proceedings as soon as you can, so that we can be early also in that kind of stage of the meeting. Thank you again, everybody, for all your contribution and interesting talks. And we will probably see each other around in some other sessions or in tomorrow's sessions if you will participate. I hope you can enjoy the meeting. Thank you again, and see you in the next sessions or in other session of this meeting. Thank you. Bye, everybody.
Thank you. Bye-bye.
Bye-bye.